Hello! In this video we are going to talk about limits. Which are the objectives of these slides or this video is to understand and review the main ideas of limits in calculus. We will also see or study some types of limits, included one-side limits and both-side limits. We will apply these ideas to some examples, and the requirements are not so much as usual. With a little idea of calculus, especially on derivatives and solving equations, we have more than enough. Okay, let's start with the definition of limits. Let's suppose that you have a function, a real function with a real variable. D is going to be the domain, and we are going to define the standard limit. We say that let A be a real number and such that there exists a delta positive such that this interval, be careful about this interval. This interval is an interval that is centered at A, but on the side, on the left, it has a little room to take points. As you can see, you have here A minus delta, A plus delta, but A cannot be in the interval. A has been taken out from the interval. So this is important, okay? And so we are going to consider this subset. Then the limit of the function x when x approaches A is going to be L and is denoted like this when x is moved between these two intervals. Okay, if we only take the right side of the interval, we say that x approaches A from the right. And when we only consider the left interval, we say that x approaches A from the left. These two limits should be equal if we want to say that the limit exists. From the right and from the left, the limit should be a value and should be equal from both sides. Okay, let's see an example. Let's see in which we have several different mathematical ideas, and it's not so difficult to understand. For example, we are going to consider a quotient in which the numerator is a polynomial, degree 1, and the denominator is another polynomial, degree 2. You know for sure, because you have been dealing with these mathematical ideas, the domain of this function are all possible values for which this function makes sense, and we need to eliminate at least 2 points. The ones that make the denominator equal to 0. Be careful always with quotients. Denominator cannot be 0, so the first thing you need to check is there is any point at which the denominator is equal to 0, and this is easy to see. That if you equal x squared minus 1 to 0, you obtain two values, 1 and negative 1. The two values you see here. Let's start calculating the limit of this function when x approaches 1. The main idea about the limits is you are going to take the value and replace in the x and see what happens. If we change x by 1, on the numerator we got 1 minus 1, and on the denominator 1 squared minus 1. So the limit you obtain is 0 over 0. This is an indetermination and should be solved in order to know if the limit exists or not. Okay. Which are by the way, there is some techniques we can apply here. 0 over 0, it's a very specific indetermination, and one way to solve it is to simplify the function as much as we can. So what we are going to do, we are not going to apply, for example, L'Hopital rule right now. What we are going to do now is to rewrite the denominator, or we are going to factor the polynomial in the denominator. So how do we do that? X squared minus 1 can be easily written as x minus 1, x plus 1. Remember that minus 1, negative 1, and positive 1 are solutions of the polynomial. So x squared minus 1 can be written as a product of x minus 1, x plus 1. Remember there is a property that the product of positive, negative conjugate polynomials is the square of the first one minus the square of the second one. But this is also just to remember this property. The key point here is that x squared minus 1 can be written like this. Therefore, the function we got from the beginning, x minus 1 divided by x squared minus 1, can be written as x minus 1 divided by x minus 1 x plus 1. I guess all of you see now that we can simplify something. X minus 1 on the numerator, x minus 1 on the denominator can be eliminated. So the function we obtain is just 1 over x plus 1. What happened if we change the function we had at the beginning by this new function already simplified? So the limit we wanted to calculate it, x minus 1, x approaching 1 of x minus 1 over x squared minus 1 is the same as the limit when x approaches 1 of 1 over x plus 1. Now, if we replace x by 1, the value x tends to, we obtain 1 over 1 plus 1, that is 1/2. So it's a real number. Therefore, the limit when x approaches 1 of this function equals 1/2. So it has a value. Okay, the natural question is, yeah, okay, we check at 1, but what happened at -1? It happens the same. We can say the same right now. Okay, we need to check. Let's see. When we calculate the limit when x tends to -1, we do the same trick. Let's solve it. Let's replace x by this value directly. So we got minus 1 on top, minus 1 squared, minus 1 below on the denominator. Minus 1 squared, be careful, is 1. Therefore, 1 minus 1 is 0. But on the numerator, we got minus 1 equals -2. This is infinity. This is not an indetermination. When the denominator tends to 0, this fraction tends to infinity. So the limit is infinity. What does this mean? This means that at this point, at -1, the function has a vertical asymptote. Do you want to see this vertical asymptote? Looks like this. At -1, the function has a vertical asymptote. It's a point, it's a value in which the function is not defined. When, as you can see, when the function approaches -1 from the right, the function tends to plus infinity. And when this function, when x approaches -1 from the left, the function goes to minus infinity. This is the typical case of a vertical asymptote. What happened at 1? 1 is almost there. When we approach from the left and from the right, the limit is 1/2. If we just make zoom on this graph, what we will see is there is a value in between that the function is not defined at 1. But from both sides, the limit is 1/2. Okay, let's see another example to finally to finish this video. In this case, we are going to take the Heaviside function. The Heaviside function is a very typical function in mathematics that is defined as you can see here. 0 if x is lower than 0. That means that the function comes here when for the negative values, the function is always 0 and goes on till minus infinity. But at 0, you have a jump, a gap, so the function equals 1 from 0 till infinity. So from 0 till infinity takes the value 1. So as you can see, it's like a stair. We are taking the value 0, 0, 0 until we reach 0 and then jump to 1 and keep going. Okay, is this function, what is the limit of this function when we approach the value 0? And we are going to do it from the left and from the right, as you can see. If we try to calculate the value when x approaches 0 from the right, then the function from the right, remember that is equal 1 all the time. So it's the limit when x approaches 0 of 1 all the time. So the limit is 1. There's nothing to replace. When we approach from the left, the function is always 0. So the limit of 0 is 0. So as you can see, both limits exist from the right and from the left, but they are different. That means that the limit does not exist. Okay, finally, it's something I mentioned before, but let's finish the slides with this theorem. We say that the limit of a function is equal to L when x approaches a if and only if both limits, the one from the right, the one from the left, exist and they are take the same value. Okay. Finally, just one more example. Try to calculate this limit. Remember that, be careful, because this value is 3. When x approaches 3 from the right, Then, as you can see, if you replace 3 here, it's 6 over 0. And this is infinity, but we need to know if it is positive or negative. How do we know? If we approach from the right, we take a value to the right of 3, like 3.1, 3.2. If you replace here, you will obtain the sign of the infinity. The same happens with when we try to calculate the limit from the left. In this case, we take values from the left of 3, 2.9, 2.99, for example. But when you replace in the function, 2.99 minus 3 is negative. So that is the reason we put negative infinity. As you can see, here is the representation of this function. When we approach from the right, it goes to plus infinity. When we approach from the left, it goes to minus infinity. What have we seen in these slides? We have reviewed the idea of limit in calculus. We just saw some examples in which we have seen a vertical asymptote and what happened to the limit to the right, from the right and from the left, and some applications of these limits. I hope this is helpful for you guys, and thank you for your attention.